So let's dive right into this explainer and trace the incredible, literally millisecond-long global adventure that kicks off every single time you browse the web. We are all online every day, right? Working, streaming, chatting, but the sheer physical and logical complexity of how our data actually travels around the globe, honestly, it's nothing short of a modern miracle. Now, think about what actually happens in those milliseconds after you click a link. Most of us just click, wait a fraction of a second, and boom, the page is there. We're completely unaware of the massive physical and digital infrastructure that just sprang into action. It's easy to think of the internet as this magical, invisible cloud, but it is very much a physical reality. Hitting enter kicks off a highly coordinated process that bridges global distances practically instantly.
But before we track this journey, we've got to introduce our hero, the data packet. You see, data doesn't just move across the internet as one giant file. If it did, we'd be dealing with massive digital traffic jams constantly. Instead, it gets chopped up into these tiny fragments. Think of them as little digital suitcases. Each packet carries a tiny piece of the actual payload, along with crucial routing info like the sender's IP address, the receiver's IP, and a sequence number. It's a system that makes data transfer so much faster and incredibly reliable.
This whole global journey really breaks down into 3 core steps. First, the data request, where your device figures out exactly where it needs to go and asks for the info. Second, the transmission. That's the rapid cross-world transit to a distant server. And third, the response, where the server chops up the requested data and fires it right back to you. Let's break down exactly how this all plays out.
Okay, part 1, the click, names and addresses.
Let's start at the very beginning, the call to adventure, right there on your screen. We have to figure out where our packet actually needs to go. Now, to send a message to any computer, you need its unique identifier, its IP address, which is just a long string of numbers. But let's face it, we humans are terrible at remembering random number strings, so we use human-readable domain names. And this is actually a huge shift in how the internet evolved. Back in the original 80s architecture, IP addresses were these stable, permanent identifiers, and the network just routed directly to them. But today, the domain name system, or DNS, steps in like a super-fast, dynamic phone book. When you type in a URL, your device first asks a DNS server to translate that name into an IP address. So in our modern reality, DNS names are the true identifiers, and IP addresses, they're just temporary, ephemeral locators used for routing. Moving on to part 2, chopping data into packets. So here's the crucial thing. Once we have that destination IP address, your massive data request absolutely cannot travel whole. It's got to get chopped up and packed into those tiny data packets we mentioned. But how does your computer know how to pack this digital suitcase so the wider network can actually read it? Well, it uses the TCP/IP model. Think of it as a 4-layer cake that wraps your data in routing instructions, sender details, and sequencing rules before it ever leaves your house. At the top, the application layer generates the data using protocols like HTTP. Then the transport layer uses TCP to chop it into sequenced segments. Down to the internet layer, which slaps on that destination IP address. And finally, the link layer formats the whole package for your actual physical hardware, like your Wi-Fi or Ethernet. It is literally a perfectly organized digital assembly line. All right, part 3, routing through the network. Let's look at the next phase. Our perfectly packed data packet leaves your device and finally hits the digital highway, entering an architecture built purely for maximum resilience. First stop, your router. Basically, the router is your local traffic cop, or like a room organizer, deciding which device in your house gets what traffic. From there, it shoots out through your modem. The modem is the physical door to the wider internet. It translates your network's digital signals into a format that can travel over the vast telephone, cable, or fiber infrastructure outside, linking you straight to your internet service provider. And you know what's really wild? How long this core idea has been around. Way back in 1973, internet pioneer Louis Pouzin described this exact concept of linking different networks together using gateways. He actually called it a catenet, a system of concatenating networks. Those early gateways, they are the direct ancestors of the modern routers that our packets are bouncing between right this very second, hopping seamlessly from one ISP network to another. The absolute genius of this original design is its resilience. It relies on something called stateless packet forwarding, meaning there is no fixed pre-planned track for your data. The network layer itself is kept intentionally simple. Every single router your packet hits just makes an independent split-second decision on where to send it next, purely based on that destination IP address. Because of this, if a router or a whole network element suddenly goes down, your packet just dynamically finds a new path. They pushed all the complexity to the edges of the network, which keeps the core incredibly resilient.
Which brings us to part 4, the deep sea journey. Once your packet clears your local network and bounces through a few domestic routers, it hits the most hidden, fascinating part of its journey. It dives, literally, into the abyss to cross the globe. Guys, it is mind-blowing to realize that 99% of all international internet traffic doesn't travel through satellites in space. It travels through physical cables lying right on the bottom of the ocean. The cloud is quite literally under the sea. Right now, there are over 600 active and planned submarine cables resting on the ocean floor, forming the absolute backbone of all global communication. Now, you might be wondering, why cables instead of satellites, right? What about Starlink? Well, it all comes down to speed and sheer capacity. These fiber optic cables shoot our data packets across entire oceans as literal pulses of light. They use a physics principle called total internal reflection to bounce that light flawlessly along a tiny glass core. This gives us wildly lower latency, meaning practically zero delay, and massive, massive bandwidth capabilities that satellites just can't match. And that bandwidth is absolutely critical for things like modern AI and cloud computing. But because this is a physical reality, our packet's journey is actually pretty dangerous. We're talking an estimated 150 to 200 cable faults happening globally every single year. These cables get snapped by dropped commercial ship anchors, fishing equipment, and even natural hazards like deep-sea earthquakes. Plus, there's the very real, rising geopolitical threat of subsea sabotage and espionage. And repairing a cut cable? Not easy. It takes highly specialized ships and deep-sea robots, and sometimes it can take months just to get them deployed to the right spot in the ocean. We actually saw exactly how this impacts our data packets recently, when physical damage hit strategic choke points, like the 2024 incidents that cut the CME-WE4 and IME-WE cables in the Red Sea. It puts a massive strain on connectivity between Europe and Asia. The network gets instantly congested. But thanks to that resilient stateless routing we talked about, our packets don't just die. They are forced to detour. They take much longer, slower routes, which ultimately just means a bit more latency for all of us users. And finally, part 5, arrival, reassembly, and display. So, after navigating past all these deep-sea threats and bouncing through a final maze of distant routers, our packet finally hits the destination server. The epic quest is over. Well, almost. Because arriving isn't the end of the story. Remember, our packet is just one tiny piece of a giant puzzle. And since packets take different dynamic routes, they almost always arrive completely out of order. This is where the receiving server leans on those transport layer rules we mentioned earlier, specifically TCP. The server checks every single packet, uses their sequence numbers to put them back together in perfect order, and if any piece got dropped along the way, it quickly asks for it again. Once everything is perfectly reassembled, the server seamlessly displays that web page or video right on your screen. And here is the crazy part. That entire process, the DNS lookup, packing the TCP IP layers, the dynamic routing, shooting pulses of light across the bottom of the ocean, and the final reassembly, all of that happens in mere milliseconds. So next time you hit enter and a page pops up instantly, just take 1 second to appreciate the miraculous ocean-crossing gauntlet those tiny data packets just survived. It really makes you wonder, doesn't it? What other incredible physical infrastructure is hiding right beneath our feet, completely invisible to our daily digital lives?